So in class, we actually skipped one of the problems from the Lesson 8 lecture, and that is about how to find the maximum speed you can travel along a banked track. So if you've ever been driving along and you exit the freeway and you notice that it's got a curve to it, the curve is not flat road, but actually tilted. This is also the same thing that you're going to see at like a racetrack like the Daytona Speedway. The track is tilted. And that actually helps keep the car in place as it is following that curve. Here I've actually gone ahead and inserted a picture of my free body diagram. I gave you that picture already so that you could see it nice and clear without any wobbly handwriting. So we can sort of see. This is the banked track. This is actually a snapshot, and the car is coming straight at me right now. We have my force of weight, which is straight down. My normal force is perpendicular to my surface. And my friction is actually keeping my car from sliding down the surface of the track towards the center. So that's sort of where we have things going. So those are the forces actually acting on the car. When we add all those forces together, we get this green force here. That's that F net. And as we know, using universal circular motion or uniform circular motion, that F net sort of relates to that mv squared over r. The only other sort of thing I wanted to highlight here is all of these angles in here. The angle of my ramp does correspond to this angle in here. Again, that's something we're sort of used to. That's going to correspond to this angle in here and this angle in here. You would use alternate interior angles and some geometry to sort of figure that out. The last thing I want to highlight is this is my sort of what direction is up, what the direction is positive here. Normally you would see me tilt this to match the angle of my incline. That is not going to be true here. My F net is entirely in my X direction, and that's going to make my life way easier when problem solving. So that's why I've done it that way. So we're going to take a look at how to actually find the maximum velocity that my car can go and still stay on the track or not go careening off. So like I said, we are going to look at the fact that my F net is going to be the sum of my forces acting on my particular object. My F net, like I already sort of established in my picture, is in the X direction. We also know that F net is equal to the mass of my object times my acceleration. This acceleration is the centripetal acceleration because it is moving in a circular path. We can also look at that as being the mv squared over r that we discussed in class. So we know that our F net is going to be that mv squared over r. We also know that that F net is going to be the sum of my forces in the X direction. So we need to take a look at what are my forces actually acting in the X direction. So some of my forces in the X direction, that's an X, guys. We need to take a look at that. Well, I do have some of my my friction. All right, so my friction is in the X direction, and some of my normal force is in the X direction. So those are my two forces in the X direction that I'm going to see. So it's my normal force in the X plus my friction. Now, it is important to note what kind of friction we are dealing with here. It is going to be our static friction because we don't want our car to slide. All right, we want it to stick. And that's how much of that is in the X direction. We already established the fact that my F net is equal to my sum of forces in the X direction, and my F net is also equal to this. So we're able to now plug this in over here. So my mv squared over r is equal to my sum of forces, that force of my normal that's in the X direction, and my amount of static friction that's in the X direction. All right. Leaving my left-hand side alone, I'm going to start sort of replacing my right-hand side with the information that I know. When I break my normal force into its x and y components, right now I'm only interested in the x components. We are going to use sine because it is opposite from the angle that I've labeled here. So my mv squared over r is equal to my normal force times the sine of theta. And my static friction, as you know, in the x direction is going to be my static friction times cosine, because that's my adjacent side in this particular case. We can also look at the fact that that static friction has a particular value. That's going to be that coefficient of friction times my normal force. So I'm going to go ahead and sort of rewrite that out with that new information. So again, keeping my left-hand side the same. My normal force times the sine of theta plus my coefficient of friction times the normal force times the cosine of theta. So we can see the fact that in both terms I do have that normal force present, that Fn is in both terms on the right-hand side. So my mv squared over r is equal to my normal force times sine of theta plus mu cosine of theta. So that cleans that up a little bit. Our ultimate goal, as you remember, is going to be that velocity squared. While we're still having some unknown terms happening here, that normal force is something we don't actually know. So we need to go back to our other direction, because we've just been dealing with x, to find that normal force and that y. So I'm going to jump over to some blank space that I have over here and know that we need to find Fn. Right? So we are going to look at the sum of the forces acting in the y direction is equal to the mass times the acceleration in the y direction. We're not seeing any movement up and down on the ramp. We're just sort of having that it stay in that same plane as it goes around the corner. So my acceleration in the y direction is 0. We're then able to sort of continue to flesh that out. What we have going on in the y direction, let's go back to our picture here really quick. We have our weight down, we have some of our friction which is down, and we have our normal force up. So keeping track of those, we're gonna plug this into our equation on the left-hand side. My normal force is up, so force of normal y minus my force of weight, which was straight down, and we didn't have to break that into pieces. It was the only one that was in one dimension. And our force of static friction in the y, we did have some of that, which was down. And remember, my right-hand side was 0. My force of normal in the y, where before it was our sine, now it's going to be our cosine. So force of normal times cosine of theta. We know the force of weight is mg. And our force of static friction is going to be that, in the y direction, is to be the force of static friction times sine of theta, and that's all equal to 0. Just a reminder, that force of static friction is equal to mu s times our normal force, or our Fn. That's not new. That's the same as it was before. And we're going to continue to sort of do some algebra to clean that up. So my Fn times cosine of theta minus mg minus mu s times Fn times sine of theta is equal to 0. Remember, the reason we were doing some of the forces in the y direction was to get that normal force by itself. So I'm going to subtract my, or add my mg to the other side. So I have Fn times cosine of theta minus mu s times Fn sine theta is equal to mg. So factor out that normal force. Whoops, skipped a step there. All right, and now we're going to divide away that cosine theta minus mu sine theta from both sides. That gives us the Fn, the normal force on its own, and that looks like this. All right, so with this information, we're now able to go back to the equation we saw before and where we had the normal force, substitute all of that in. All right, so this is going to go in right there. All right, so keeping my left hand side of my equation the same, I have mv squared over r, where the Fn is now going to be the mg. And this is all over the cosine theta minus mu sine theta. Right? So, but my upper is going to stay the same. So sine theta plus mu cosine theta, and that's all over the cosine theta minus mu sine theta. All right, so noticing this, you will see the fact that I have mass on both sides of my equation. Because I have mass on both sides of my equation, that term does cancel. Bam! We were doing this to solve specifically for v, so we're going to multiply both sides by r. All right, when we do that, I get the fact that my v squared is equal to gr times sine of theta plus mu s cosine of theta, and that was all over cosine of theta minus mu s sine of theta. All right, and there's only one more step missing, and that would be to take the square root of both sides. When I take the square root of both sides, that square root stays on the right-hand side, and then the square sort of leaves on the left-hand side. So I'm going to rewrite it one last time. My maximum velocity that I can go around a banked road is equal to the square root of gr times sine of theta plus coefficient of friction times cosine of theta, and that is all over that sort of difference, that cosine theta minus us sine of theta. All right, so this is the maximum speed on any banked curve with a consistent radius. You just need to know the coefficient of friction for those particular tires, and then, of course, what the angle of that banked road is. All right, thanks.